Hi guys. So I wanted to talk a little bit about, capacitors. I want to get to the equation for the capacitance of a parallel plate capacitor. But to do that, we're going to need to go backwards a little bit and make sure that we understand, at least at a qualitative level, potential, and more importantly, potential difference. And so what I'm showing you is that investigation we did on FET in electrostatics, where we were looking at these equal potential lines. If you recall, the idea was that you were tying it back to gravitational potential. So kind of looking at like a terrain map. And if I took this picture and drew it kind of from a side view, so, we're looking at it, kind of on edge this way, then basically taking the terrain map and making actual like a mountain and a hole, then what we can see is that we have a very high potential where the positive charge is. And as we go across, that's decreasing until it reaches zero, and then it becomes very, very negative over on this side. So for a dipole, what we'd end up getting is kind of I'll put a positive charge here, and the negative charge then would be down here. And so what we get is a kind of, this would be more like a mountain, which then goes over to a hole, like that. And this would be on, kind of both sides. So kind of do it like that. Okay, this side I didn't draw very well, but you get the idea. And then our equal potentials would be, wherever the potential is the same. So like that. And likewise, you know what, I'm going to erase this and redraw it so that we get that funnel shape a little better. So then this would dip down into a hole. So that would be a negative charge. This would come out this way. Okay, so then we can think about what's going to happen to charges if we place it in this field. So these represent, again, the potential, which can be thought of as sort of the strength of the field at that point. So if we were to put a positive charge, a test charge, remember these are source charges. So that's a source. So I'm going to ignore the negative over here. So we're just considering this right here. Since these are like charges, they're going to repel. And so the field is going to push this thing down the hill. And so a positive charge behaves kind of like just a ball in a gravitational field. If we put it on a hill and release it, it's going to start moving. And this one would actually move all the way across and then down into the hole. And so we would get motion of this positive charge. The weird thing is that negative charges are opposite. So the analogy kind of breaks if we're talking about a negative charge, because a negative charge is attracted to positive. So these actually roll uphill. So you can think of it over here. If I had a negative charge and put it here, then it's going to repel. So it's going to move this way. And so negative charges move to higher potentials and positive charges will move to lower potentials. Now potential is, we can use it, but it doesn't really tell me a lot. Because if I told you that, let me think. If I just told you this point in space has a value, has a potential of say 5 volts. And then I say, okay, let's put a positive charge there. Can you tell me what's going to happen? Well, the answer is no, because you don't know what's surrounding it. Is this the bottom? Does it kind of do a dip? Are we at the top of a hill? Are you on the side of a hill? Which way is it going to move? We don't know. We have to know what's going on next to it. So we got to know, like, maybe this is 3 volts. And so then I know that the positive charge would move this way through less potential. And so it's not really potential that we need. It's the difference. It's the potential difference. And this is the key. So potential difference, which we can call voltage. I'll probably always call it potential difference, but if you say voltage, that's fine, because that kind of tells me which way things are going to move. It tells me a lot more information than just a single number. So we'll talk a lot about potential difference. Now I want to go back to this because this will build up some things with capacitance. One thing we can think about is like what's going to happen if I start adding a bunch of charge. So if I like doubled or tripled the charge over here, what would happen is it would just make a bigger hill. So if I had like 3 times that charge, I might get something like this. So it's going to be really, really steep, like that. And so what I can see is that increasing the charge will increase the potential difference. It's because I'll get a much steeper hill. So I'll get a bigger change between them, or not between them, but it just makes a steeper hill, trying to make this all qualitative. So this will increase the potentials, which in turn increases the potential difference. So we can see that the potential difference is proportional to the charge, and that just kind of makes sense. It'll either make a higher hill or a deeper hole. And in addition, one of the things that we talked about in electrostatics is the electric field. And so the field goes across this, and we should be pretty comfortable that if I have much more charge, I'm going to have a bigger field. I'm going to get a bigger electric field. And so both the potential difference and the electric field are proportional to the charge. And we'll come back to that in just a second. So we kind of want to think about how we could harness this. And that's one of the activities we did. Actually, in the simulation, I think you did it. You had to make a line of charge, a line of positive charges, a line of negative charges, and then we were looking at kind of in between. Because by doing so, what we do is we create a uniform field. That means that it's just in the same direction, same strength over a given distance. So let's look at that. So again, what we're trying to do is create a uniform field. And one way of doing that is through a plate of charge. So we take a bunch of charges and we just line them up like so. And we're ignoring the width. So we're just saying that there's a bunch of positive charge here. Then what we learned is that this will create an electric field which goes directly out. Now, it's an infinite sheet, so we're ignoring the edges. But we would get an E field which kind of goes, off in this direction. I'll just draw 3 because I won't spend all my time drawing. So it would go out in each direction. And then we learn that for an infinite sheet like this, that the electric field, so the E field, was a sigma over 2 epsilon. We'll come back to this. And so this is good, but what we want to create is kind of a contained one. So what we can do is we can add a second one of negative charge. So we'll put another plate next to it, but this one will have negative charge. And we can kind of get just qualitative, and then I'll go through some derivations. So this one has a big negative charge, but it's the same. It's the same as this other side. So this is like negative Q, and this would be positive Q. So this plate over here is going to generate a field that comes into it. So what we'll end up getting is this goes into this plate, like that. This was that, we did this activity in class where you were going through this. But now it might make more sense because this is going to become our capacitor. Okay, so analyzing this, what we can see is that over here, the field, remember, it's uniform. So it's the same strength. So like this little piece of strength is equal to this piece of strength, but they're in the opposite directions. So these cancel out. Likewise these. So this entire field over here is 0. Because everything cancels out. So the net, the total field on this side. Likewise over here, we're going to have the same strength field but in opposite directions. So the total field on this side is 0. And so what we end up with is we just have an electric field inside. Let me see if I can, it might be best if we just start erasing all that, right? So it's not so busy. But what we've done is we've established a uniform electric field on the inside. And the strength of the field is, that's what we're gonna look at. So we know the strength of one of them is given by this equation. So we could say that that's the electric field generated by the left side. And notice that these are in the same direction. So they're just gonna add up. So the strength on the right, the electric field on the right is also sigma E over epsilon naught. And so if we add these, it would just be, twice this. So we would get the total electric field inside of here. We'll call that E total, or I don't know, E inside there. E inside is equal to, remember that's charge density, and charge density is the charge per area. So we get the charge density over 2 epsilon naught plus charge density over 2 permittivity. So we get the inside of these two plates is going to be 2 sigma over 2 epsilon naught, which simplifies to sigma over epsilon naught. Okay, so what this is the strength of the field inside of this capacitor. Now the thing is, here we'd have to have charge density, and so we may not know that, and typically we'll have it in terms of charge. We'll know the charge on a plate. So we can redefine this because sigma is this, and so we get this. The electric field strength is equal to the charge over the permittivity times the area, and this is what will be more useful. If we know charge density, we can use this. But this is the E field, uniform E field, in a parallel plate capacitor. I don't know if that's how you spell it. Parallel plate capacitor. Okay, so we can see that if we increase the charge, that's going to increase the electric field, and that's kind of what we were saying before. But then we also have this dependence upon the area. Okay, so before we go further, we can think about the charge. So the E field is just dependent upon the charge, and going back through our derivation, the sigma is the charge over area. So what we're looking at is just the charge on one of these plates. And it doesn't matter which one we're looking at, whether it's positive or negative. It's just the magnitude of one of the plates when we talk about the charge. So in a capacitor, it's kind of the charge in the system. Physically, it's the charge that's stored on one, because the total charge here obviously is 0, positive Q, negative Q. So when we move into the capacitors, keep that in mind. We just deal with one of them because it's the amount of charge moved from one plate to the other to create the imbalance. Okay, so now we want to get the potential. We want to think about the potential difference. And when I say potential, I'm also talking about potential difference. Like, again, because talking about just the potential isn't very useful. So if we think of this as the top of the hill, and this is the bottom of the hole, then we clearly have a potential difference across these plates. And that would be delta V. And then we have a uniform field inside. So we know how these are related. We know that the potential difference is the E field times the distance between. So D would be the distance as well. So D is also like this, the distance between the plates. So now what we can do is we can take, this is only valid for a uniform field, but that's what we have. So now we can use this over here. So we'll get that the potential difference across the capacitor is going to be Q over epsilon naught times A times D. Now, what I'm going to do is I'm going to move this stuff around because I want a relationship between the charge and the potential difference. That was the idea. So if I do that, I can move the Q over. So we would get delta V over Q is equal to, or wait, that's not how I want it. I want Q to delta V. Let me redo this. Because it's the charge that drives the potential difference, not the other way around. Like when we started adding charge, it makes a higher hill, so we get a bigger potential difference. So we'll move this one down, this one comes up, so we get epsilon naught times area, and then we would divide the D is equal to Q over delta V. So let's think about this. Okay, so what I did is I multiplied this over, brought this down, and then divided by D. That gave me this. So let's think about what this statement means. Basically, it's saying everything over here, if I hold it constant, so the area stays, in other words, I'm not changing the characteristics of this. I hold the area constant and I hold the plates the same distance away. Then the ratio of the charge to the potential difference is always the same. You know, this is constant. In other words, if I put on more charge, the potential difference will increase correspondingly, such that this is always the same because these are all constant. So we can redefine this. We can call that something else, and that's what we call capacitance. And so we'll define out of this, we're going to say that we're going to call this thing capacitance, and capacitance is just going to be the Q over potential difference. So it's a definition, so we could put 3 lines. And if we do that, then we end up with capacitance is A epsilon naught divided by the distance. So this right here is the capacitance of a parallel plate capacitor. Capacitance of a parallel plate. I'm just going to put parallel because I can't spell it. Plate capacitor. And so what we can see, I don't even know if I spelled that right. No, capacitor. What we can see is that the capacitance depends only on the area of the plate and how far apart they are. So the capacitance is proportional to the area, meaning that if the area goes up, the capacitance goes up. And it's inversely proportional to the distance between them. So as the distance gets bigger, the capacitance gets smaller. So I'll ask you some questions on this following this video. But basically this was just to get through to this capacitance of a parallel plate capacitor.